Okay, the conservation of momentum. Balancing the books. Here you see an example of a Newton's cradle, a great conservation of momentum device. So, what does the conservation mean? It means the total energy, the total amount of momentum in a closed system will always remain constant, just like the conservation of energy that we learned earlier in the course. It's stated simply as P before equals P after. That's all that really appears on the reference table. So you have to be able to take that equation and derive out of it. So you take all of the momentum of the objects before something happens, like a collision, and it must equal all the momentum for all the objects after the collision. So let's take a look at that, what that looks like. Here's an elastic collision. When two objects collide and separate without sticking, if they have the same mass, they just trade momentum. That was the Newton's cradle you saw earlier, or in this animated example you see above. Let's try an example problem. A 2-kilogram ball moving at 3 meters per second collides with a 3-kilogram ball at rest. Assuming that the 2-kilogram ball stops after the collision, what's the velocity of the 3-kilogram ball after the collision? Again, P before equals P after. So we take the momentum before. Here you see M1 V1I, that's 2 kilograms times positive 3 meters per second. M2 V2I, since it was at rest, it's 0, equals, this one comes to rest afterwards, M1 V1F, plus 3 kilograms times V2F. We're solving there, we got 2 meters per second. So here's an elastic collision. Elastic collisions are when two objects collide and stick together, as you see here in this animation. The two masses of the objects combine to form a single mass. Again, P before has to equal P after. So let's try this example. A 5-kilogram cart moving at 6 meters per second collides with a 10-kilogram cart moving at negative 6 meters per second. If the two carts stick together during the collision, what's their final velocity? P before equals P after. So M1 V1I plus M2 V2I equals M1 plus M2 times some new final velocity. So again, looking at the numbers here, you see that the final velocity is negative 2 meters per second, meaning it'll move in that direction. Remember, the negative sign is just a direction. Momentum is a vector, just like velocity. Finally, an explosion or a pop apart. Two objects held together are pushed apart. So in this particular example, usually the momentum is 0 when it starts. In this bomb, for example, the mass of this side of the bomb momentum and that side of the bomb's momentum has to be equal because they are going to have 0 momentum before and 0 momentum after. Let's try an example of recoil, which is very common for separation or pop-apart problems, explosions. Here we have a cannon, a 100-kilogram cannon with a 5-kilogram cannonball. When a cannonball is fired, what happens to the cannon? Well, the momentum before is 0. So if the cannonball is going to be fired in one direction, the cannon must move backwards, and we call that recoil. If the cannonball has an initial velocity of 20 meters per second, what's the recoil velocity of the cannon? So again, P before has to equal P after. 0 before, because before the explosion, they have 0 total momentum. So if the cannon gains positive 100, then if the cannonball gains positive 100, then the cannon must gain negative 100. So it must move backwards at negative 1 meter per second. So that's the conservation of momentum, gang. See you in class.